Okay, good afternoon. Michael Stadler here. I'm here with our lead engineer, Zach Pasanek. We have also our director of sales, Brad Miller. And of course, we have Jay here, who was organizing this and is our marketing person. I was thinking that we actually have 10 or 15 minutes at the beginning here to set the stage for Xendee, what Xendee is, and what we can do with Xendee. And then I will jump into the case, and you can watch me to build a couple of different technologies into the case and how we run it, and we can also then discuss the results. We can have, of course, questions. So let me start here, and if they're really pressuring questions, then just let us know. But if it's not that important, then maybe we want to have them at the end, because there are a couple of people in this room.
Feel free to put the questions in the chat as well, by the way, and we'll be here with another engineer, Zach, to help answer those questions.
That's right. Okay, so when you do a microgrid project, there are of course different layers and different levels what you have to do in it for a design. I'm not discussing all these detailed things, but the point here is you probably will start with a conceptual design, and a conceptual design basically involves to figure out if a microgrid might make sense for a certain location, campus, building, whatever it is, right? And typical results on a high level, what technologies you should consider, and how much money you could save here. Then you go into a more detailed design in which you consider already changes over time, because if you want to have a very reliable result, then you probably have to model your microgrid 20 or 15 years into the future to make an assessment about changes and how this will impact your revenue stream. You can already start thinking about engineering capabilities here and features like very simple one-line diagrams and power flow. And then when you have all this defined, then you go really in very deep power system one-line diagram design, where you really think about motor starting, short circuit analysis, and then also transient analysis. Our platform doesn't provide transient analysis for the clients. We do this internally. But the thing is that transient analysis is really a very complicated field, and we decided if someone needs it, and we can help you on this. But at this point, we are not really settled on how we will bring this into the platform. So as already said, we have the conceptual design, the technical design. Then of course, there's actually also an implementation. So if you're really serious about this microgrid design and you want to implement it by yourself because you're a construction company, engineering company, then you probably also want to track the progress. We have also software for this. We're not talking about this today, but the Federal Aviation Administration, for example, is also using our software to implement microgrids. One thing that we're not talking about, but is really important, is the control and operation of microgrids. And we use the same technology like for the planning. And the reasoning for this being is, if you plan something, then you want to make sure that you control it in a similar fashion, because otherwise you really cannot guarantee the results that you were actually planning for. And this is why we have one platform. And later this year, the control and operational part will be released. And then it's a software-based system. You can actually run microgrids or distributed energy resources in the same way like we were planning for, and that's what you see today. Key here is actually the one platform to make it faster and cheaper. As I started doing this, as I was still working for the government in Northern California, I was working for Lawrenceburg National Laboratory. I mean, in 2013, 14, a microgrid project was $500,000 just to figure out what technologies from a conceptual perspective should be actually considered in a microgrid. We really brought this down a lot. I mean, now we can do this really in a couple of days, and standardization is really key here. And you will see this with the platform, that we have a lot of databases, interfaces, which will help you to actually bring data in. Last year, we also won the Edison Award in Gold for critical infrastructure. And one thing to note about us is we really try to work very closely with the clients, and this gives us the possibility actually to improve the tool by learning from you guys, and at the same time also respond very quickly to requested changes that you might have. And it's a cloud-based system. Every other week we're releasing a new version for bug fixes, and this really allows us to really respond very quickly to requests or changes that you might want to have for your specific cases here. Before we go into the model, data. I mean, I already had a couple of questions around this. What data is really needed here? And I would say the most important data is actually the load profile. And you just don't want to have an average load for the full year. You really want to have at a minimum 8,760 time steps so that you can model load shifting and all that stuff, and that technologies can respond to different electricity rates, which are often in combination with higher demands, really important here. So load profiles are really important. We have databases in Xendee helping you on this, but the more details you have on the load profiles, the better it is. Is it okay how I'm coming through here? Everything okay? Just checking in here because I have no feedback here, and I don't see
very
anyone.
clear. Very clear.
Okay, good. Okay, thank you. When I'm running my presentation, I don't see you guys, or so I'm just looking at my presentation. This is what I'm asking here. The other thing is really the tariff, and we have here, and you will see this, really interfaces which will help you to really collect the information in a simple way. And then, of course, you have to combine this, if you have them, with already existing technologies. So you might already have some technologies, a CHP system on site. You might already have a PV system on site. And then you combine it with technology options and technologies you might be interested. And then you have a certain objective here. And the objective is actually either cost minimization, CO2, increased resilience, and so on. And then Xendee is actually delivering you the capacities, the operational schedule, and this is key, and we'll talk about this, and also where to place these technologies, because Xendee already combines economics with distribution system modeling. Maybe Zach, you want to explain this diagram?
Sure.
And we focus on the dispatch, and then we move on. Thank you.
Sure. Thanks, Michael. So as Michael was saying, the goal of Xendee is to combine as much of a microgrid design into one platform as possible. There's a lot of different parts. And this diagram tries to represent the planning component of that. It looks very complex, but it's actually probably the simplest representation of the complex math behind Xendee that you can do. So on the far right side are end uses. As Michael mentioned, there's certain data you need to put into the model. One of the most important pieces of data is the end uses. And we actually break those out into a lot of distinct end uses. So we have cooling and refrigeration load, which can be completely separate from your electrical load. You can break the heating load into several different heating levels, as well as have fuel loads. The idea then is you're mapping energy to those loads, or more correctly, Xendee is optimally mapping energy and power to those end uses. And the way it's doing that is on the far left, all the way to the left, it's looking at external sources such as a utility or maybe a district heating source you have set up or a power purchase agreement. But it's figuring out how much energy it should take from the utility and how much energy it should take from on-site assets that it can then purchase, pay an annuity on, and maintain. So you can think of each of those colors as a different energy flow, and you can think of the width of those lines as the dispatch. So not only is it figuring out, how much it should do in one time step, it's figuring it out over a full year, or over multiple years, as Michael will show multi-year analysis. And you can think of the width of each of those bars as the decision of dispatch that Xendee's making. And the combination of all of those different width bars over the year is the optimal decision, the optimal investment and dispatch decision that can be made. It actually gives you a simulated IEEE 30, an IEEE basically standard controller, 2030.7, thank you. Standard controller dispatch decision, like he's showing on the bottom right. So the combination of all these decisions is actually an optimal control strategy that comes out of this model, in addition to the optimal investment capacities.
That's right. And so key here is really to emphasize this. We have basically, let's say we have investment costs and we have operational costs, right? And the objective function of building, let's say it's cost, we want to minimize costs. We have amortized capital costs, and Zach was already alluding to this, and then we have operational costs. And what Xendee does is it looks into the different technology options and then how they could be run so that we, let's say, minimize the costs against the utility. And let's say storage, electric storage might be expensive on the investment side, but if it's a very effective way to reduce demand charges, power charges, or electricity rates against the utility, then probably it makes sense to invest in this technology. And by trading off these two parts these two essential parts, investment costs and operational costs, we actually deliver this dispatch as a result and not as an input as others would do it, because we can actually, so what you see on your screen is really for every time step, the optimal solution, how you should run the technologies to achieve your goals. And at the end of the day, it makes sense, because I mean, if you get a sports car and I get a sports car, we probably have a different fuel mileage because we drive it different. That's exactly what we're doing here. And if you think about this, and if you combine this control strategy with real-time information forecast, we actually have a real control attendant. That's what we are delivering later this year. So let me just now I need to just have a movie for 3 minutes, which I would like to show here. Let me just get it up here. And that's a movie with features that I have to just reshare here because I had to start it. That has features in it which we cannot really show today, or which are too much for this short webinar. So I hope you see my screen here. You see my screen?
Yes.
Yes, we can.
The video just loaded.
Yeah. Okay. So this is really we're not doing this today. This is a multi-node setup. So Xendee really allows you to model a complete campus and extended campus, right? Somehow the quality is really coming bad through here. You see this, the quality in the same bad? No, it's better. Okay. So we can actually define load pockets here. These are the nodes, and then we can connect them with cables. And Xendee actually can do cable sizing and transformer sizing for you. So it can actually figure out how big the cable or transformer should be between the different nodes to actually handle the additional burden because of renewable resources or whatever it is, right? And everything is GIS based, as you can see. It will calculate the length for you. And here you see that we are adding a PV technology. So the goal with this project actually was to figure out if we should have a centralized PV system or if we should have a distributed PV systems. This is actually a feature where you can do site surveys, and you will see this today. So you can actually tell Xendee, hey, this is the space that I have available at each node, and then it will consider it, and it cannot be really bigger than this space. We're uploading load profiles. And I will show you this, and this is a database that I also going to show you. This is from a database. But when we have all these things, we can specify what financing methodology we're using, and that's actually really key. And I want to pause the movie here because I think not many are aware of this. So there are different methodologies on how you can assess the attractiveness of a project. I mean, you could think about amortized capital costs, right? Or you think about net present value, or you need loans from a bank to finance the system. And what we have seen here is that sometimes these methodologies get mixed up without really thinking about the impact here. And what you see on your screen is the equipment lifetime financing, which basically amortizes the investment costs over the lifetime of each technology. And this means that every technology has an equal playing field. Because if I would have, let's say, a very expensive technology, which lasts, let's say, 30 years, and then I have a cheap technology which lasts 10 years, and I have a project length for 15 years, then probably I would, in a net present value calculation, not really see this expensive technology showing up, because I would neglect all the revenue that I would get at the end of the project length, right? And this is why we have, for example, this lifetime financing, which is not project. It doesn't have a project length. It comes from the utility sector, where each technology gets basically amortized over the lifetime, and then you can, in a fair way, compare the levelized cost of each technology and figure out what is important. And in the next screen here, we can do this also then for long-term financing. But what we will do here is, in this movie, we will run it with lifetime financing, then I show you the results, and then I show you the results with a different financing methodology, and you will see that the results are completely different. And that's something which we have to keep in mind. So now we are running this with amortized capital costs approach, the lifetime. And as we can see, it tells us for each node where we have to place different PV systems and where the storage system should go, right? And then later on, I will run the same thing here in the movie with long-term financing net present value approach, and it will change the results completely. What you also see get out from Xendee is this dispatch that Zach and I were explaining early on, and you see nicely for every date type, for every node, you see how this actually changes. And this is a really interesting result. You can see that the blue bars are actually cut, which is the purchase from utility. And this basically means here we do demand charge management, and we really nicely cut it off. And if I run this with the full time series data with every day in a year, then you also get this result for every day here. So this is just a different result. You see how this changes between the different months. And of course, you can also look at different node levels here, and then you can track the energy. What also is interesting is it also gives you the voltage levels. So, I mean, you see that some nodes have some undervoltage problems and so on, and you see all the losses. Now we run this with long-term finance.
Can you pause it just for a second? I just wanted to point out with the dispatch, that result's really interesting because we didn't have to define the dispatch to Xendee, right? It knew just because it's an optimization that we needed a different dispatch in the winter versus the summer, because again, it simulates a real controller and it figures out the rules for you.
That's right. That's right. What you see now on your screen is I'm doing the long-term financing, which is a net present value calculation, which explicitly has a project length. And we are setting the project length here to 20 years, but the lifetime of the PV system, for example, is 30 years. And this, of course, will impact our results. And when we rerun this, you will see that the results changed completely here. So, and as you can see now, we have way less PV. And we have a diesel generator. So we actually, with just a different financial methodology, we completely changed the results and actually got rid of the storage system. So this is really key to consider. The last thing in this movie, and before we go into the demo, is really a multi-year analysis, which allows us to model changes in electricity rates, performance, and technology costs over time. And Xendee will then actually assess every year and figure out if a technology should be upgraded or maybe not reinvested in and so on. And in this case here, you will see that we have really that the capacity, the battery actually goes away in 2030 because of the settings that we had. And of course, this will change your revenue stream. So if you model a microgrid as a service for a client, then you should probably model this in a careful way over time with a multi-year setting so that you can be sure about your revenue stream. So let me then stop sharing this. In the meantime, if you have questions, we can answer them while I'm uploading the microgrid example here.
Again, please feel free to send questions. We've had a few good ones through the chat, and we're looking forward to answering more.
Also, looks like a lot of those questions are going directly to Zach. So if you don't see them in the chat, no worries. Zach is seeing them and responding.
Okay. Zach, do you need some time, or are we good to go?
We're good to go. I can answer in the background.
And as a reminder to everybody else, once again, this will be recorded. Also, as being here either for the live or the webinar session, you can get access to a free account with Xendee, a free trial. If you don't have access to that right now, just feel free to email Brett or just reach out to us at Xendee. We'll be sure to help you get that. But if you fall behind or anything, feel free. We're just going to go ahead and send out a recording of this after the fact. So don't worry. Feel free to follow along, and you'll be able to see it after. And our director of sales just posted his email in the chat right there for everyone to see, bmiller@xendee.com. Obviously, feel free to reach out to him or the email, which is the same one that gave you the invite for this webinar. Good luck, Michael. Thank you again.
Okay. So here I'm in Xendee already, and I will do a single node case today. So not this multi-node that you have seen in the movie, because it would be way too much. And I will just focus on a couple of aspects so to give you a feeling about how to really work with this tool. And already build a couple of icons in this system here. We already have a point of common coupling because it's a grid connected microgrid that I'm modeling. I already defined the electric storage as an option. I will explain this later on, with an electric chiller system, a boiler, because we can also not only consider electricity, we're also considering heating and cooling here. And here's, of course, the controller. I already defined this, but if I go to settings here, you will see all the technologies that we actually can consider at some point here in Xendee. And I mean, I could go with concentrated solar power. I could go with hydrogen storage if we want to do this. methanizer, heat pumps, and all that stuff. Not doing this today. And if I would toggle here, for example, electrolyzer, then I would just see the icon on the other screen and I could work with it. So it's not that I'm forcing a technology into the solution. I'm just enabling the screen in a way that it's easier to use for me, okay? So, so the first thing is really to upload load profiles here. And we have different ways of doing this. We can upload the load profiles directly, which I will do. We have a database here for the US, which is based on climate zone. It comes from the National Renewable Energy Lab, Department of Energy. And all those different colors here are climate zones. And I'm here in San Diego. And if I click this, then I could actually say, well, this is a hospital case. It's a new construction. And then it gives me typical profiles for a hospital, for the electricity, cooling, refrigeration, space heating, water heating, and so on. And here I can scale this now. I mean, if I know the annual demand for electricity, for natural gas, then I could scale it, or I can scale this also on a monthly basis. So just go here. So let's say I want to change the peak here for January, so the demand, then it would scale it up. To electricity, as you can see, it scaled it. I could also change the peaks and so on. So we provide this really, if it's a green field, you're doing screening, you don't have a good idea about logic, then you can use this. Another thing is the utility API data, which is brand new. So if you have an account with utility API, then you can provide this key and we can directly pull data from your account. And so you can pull it then through Xendee and can use that data for your clients or for yourself, okay? Today I'm going with data that we collected here. So just let me upload an electric one to 15 minutes. I can have kilowatt hours, whatever it is, and upload the load profile here. The next thing is we can do the same thing. For a thermal load profile, I'm going with water heating, also from thermal here. And that's basically just a CSV file, which holds one column with 8,760 data points. And the last thing that I'm uploading here is actually the cooling profile, because I also want to demonstrate this. And you can actually have your different units, and Xendee will convert this for you. And here we go, cooling load, upload it and have it in here. Zach, if you're not too busy with answering questions, maybe you want to explain this view and then also the time series.
Yeah, so one of the neat things about Xendee is we have this kind of dichotomy about how data is visualized and stored, right? So what Michael's showing you here is this monthly view. To be more correct, it's representative days within a month. So you can see that blue week highlighted. What it's showing is that 8760 load he has. This is what it looks like on a typical week for each month, a typical weekend for each month, and importantly, a typical peak day for each month to make sure we're accurately capturing the demand charges. So the idea is by downsampling the data, you can remove a lot of noise and have a much faster optimization. It's a nice feature that kind of only Xendee has. If you prefer to work with the time series data, that's also always living in the background. And Michael's going to go to the time series view and show you the load profile. So those downsampled date types we were just looking at have, again, this parallel time series view, and you can work with either data. And that's true for every input in Xendee, whether it's load, solar, temperature. Every input has this time series downsample data and this, the time series data and then the downsample data that you can work with either way.
So, okay,
so Michael, Michael, before we pass that off, could you go ahead and click the hide button next to that Zoom notification as well, that's popping up on our screen as well?
Yeah, I'm moving in a way so that I can control, so maybe it's
beautiful.
Okay.
Thank you, sorry about that.
Okay, I never know what you guys see here. Okay, so we defined the load profile, which is one of the most important things, as we said already. The second important thing, or equally important, is the electricity profile. And you can really go crazy, define your own tariffs here. I mean, we can define every month as a season, and you can have up to 6 time of use periods. We can have tiered rates, and we can do the same thing for demand charges. But and you can build your own catalog for this. You could use your own catalog, or we have a real-time interface here for tariffs. And based on the location, Xendee already knows that we're in San Diego gas and electric territory. So we go here, and I know that this is a tariff which is called A6 time of use. Search for this one, and I'm selecting this one. You can specify when, so there are different riders on all these tariffs, right? And you can specify when the effective date was and so on, or if you're on the primary side, secondary side of a transformer. Here we keep all the settings. The only thing I'm doing is because this is San Diego, we're inside the city boundaries of San Diego, and this will change the tariffs here. And we have this for the US, Canada, Mexico, and I believe for parts of Europe. Right, Zach? I can remember.
Yep, exactly correct.
Yeah. So as you can see, it's bringing the information. I mean, this is a tariff with a minimum 500 kilowatt demand. So you would have to check, I mean, if you're falling below this, because otherwise the utility will move you over. I'm on the primary side, and as you can see, it's a time of use rate, which goes up to 23 cents per kilowatt hour, but it has a hefty demand charge here of $30 per kilowatt non-coincident demand charge, which of course will impact the technology adoption. So takes a little bit to get this data in. And so now we have load profiles and tariffs. We save this. And next thing is really to define technologies. And depending on the settings that I have shown you at the beginning of this use case, you see the icons down here. And these are the icons that you have selected and you wish to consider. It's not that they really have to show up. It's with this, we're setting all the information here, and I'm going with a solar PV system. We could define multiple PV systems with different orientations. I'm going with a system from the catalog, 0.5 megawatt rooftop, this one, and bring the data in. What I'm also doing is I'm also specifying inverter costs, because we can split the inverter cost from the panel cost here with a 15-year lifetime. And Zach, do you want to explain the top here with consider existing, and then I go down here?
Yeah. So the key is to remember that Xendee is making investment decisions based on what you're putting on the map. And those investment decisions can come in a few different forms. So what Michael has selected right now is the option consider. That's just letting Xendee consider this asset. It's going to go figure out exactly how much you need based on the costs and your financials and your loads. There's other options to putting a technology in your model. For example, if you have an existing array, you could model the existing array and not have that CapEx hit to your model because it's an existing asset and it's already going to have some age. Similarly, we can do existing plus more, where we have an existing array. We want to figure out with this type of array, with this performance, should we add more? The last option is just to force a solution. So if Xendee is coming back and saying, hey, battery just doesn't make sense on the site, what you can do is you can force it in. You can say, hey, Xendee, because of this grant, we need 1 megawatt hour battery. So you can go ahead and force that solution, and Xendee will optimize around whatever you force in. It'll pick the best assets to go with that battery. And again, force plus more is similar to existing plus more.
One thing to note here is also the unit costs, of course, are probably changing with the unit size. I mean, a smaller system is probably more expensive than a larger one. So you could actually then model here really different unit costs if you would like to do that. I'm not doing this today, but maybe you have pricing power, whatever it is, and you could exercise this. This is what you already have seen in the movie here. Just let me zoom out a little bit here. As you can, this is the drawing tool for the site survey. So I can actually draw now available space for a PV system, and then Xendee will respect this. And I can actually say, well, this PV system has this maximum available space, but I could actually then define different PV systems and could say, well, maybe we're doing our, I don't know, this parking lot here, and it would then respect that area for this parking lot. We're not doing this. I will just enter here 130,000 square feet area. We could define here if we want to export to the utility. I'm just need to check my notes here. We're not doing this, so we want to keep all the energy on site. We'll probably support a battery adoption, right? Because if there's enough output from the PV system, we're not selling it to utility, then probably we'll see some storage here. So we give a tax credit of 26%, and we don't do macros. If you have another tool for site surveys for PV systems, you could use those tools and then upload here the PV performance data from those tools. Again, it's a kind of time series data, one column, 8,760 data points if it's a 1 hour data set, time step data point, otherwise 35,000 for 50 minutes and so on. So if you want to do a really detailed analysis with shading, so you could do this. We have also an interface here to NREL, and if I click compute, it just brings in the PV performance data for this location. And now we have defined a PV system as an option for our microgrid. I already defined storage here, and I also took it from the catalog. Same structure like Stack was explaining. We've considered existing plus more. Of course, there are different technical specifications down here. A couple of them, probably you cannot purchase batteries in any size. So this is why we have this unit size here. So this is a battery which can only be purchased in 600 kilowatt hour steps, 600, 1200, 1800, and so on. Maybe the battery doesn't like if you discharge it below 25%. So you could enter this here. And then in an emergency situation, you probably could discharge to zero, right? For warranty reasons, there might be a maximum number of cycles that you can do per year, so you could set this. There's also a minimum annual cycle. This comes in with a California SGRP program, for example, in which you have to cycle, I cannot remember the number, but a couple of hundred times a year to actually be eligible for a subsidy. So anyway, I mean, we can also say charge from utility if we want to do this, if we want to use the battery for sales back to the market. So not only back to the utility, but here we could also model and zero services and so on. I'm not changing anything here because we already have this. So we have only two things to define here, electric vehicles and a natural gas generator, and then we're ready to go for an optimization here. So let me define the electric vehicle here. And there are different ways of doing this. I mean, you might already know roughly on how you think you want to charge your electric vehicles. Then you will upload this profile. But in reality, that's not always the case. And sometimes you also want to model electric fleet and an EV fleet. And this is what I'm doing here. This is a hospital in San Diego. And what I'm going to model is actually employees coming in to work in the morning, plugging in their cars, and then requesting a certain amount of energy for the electric vehicles before they leave. And with this, we can give Xendee some flexibility to minimize costs and at the same time provide that energy. So what I'm doing is I'm forcing 10 charging stations here because we just made up our mind. I mean, I could also go with consider as we did it before, but I'm just saying, well, we want to have 10 charging stations with 50 kilowatts. We have to provide some basic charging efficiencies numbers. Let's say I charge this for $10,000, and we're not selling it because these are our employees. I mean, you could model actually also sales here. I mean, if this is a shopping mall, then you could actually put in a certain dollar per kilowatt hour amount, and then it would be an additional revenue stream for the microgrid. In this case, we're giving it away for free. But what we are saying here is actually that between midnight and 5 in the morning, there's no car connected, so it's pointless to think about charging these cars, right? But then let's say at 6 in the morning, the first cars are showing up, and let's say 50% of our staff is around, starting at 6 in the morning. And this goes until 9 o'clock, and then starting at 10, everyone is in, and then they start leaving again at 8 p.m., right? So basically, this is a kind of availability when the cars show up, right? And if we take the area underneath this yellow line here, then we could charge basically the cars with 5,950 kilowatt hours. But maybe we know based on a survey or feedback from our employees that we don't have to charge the cars that much because they're only maybe going 30 miles a day. So let's say if we say, no, we only want to charge the cars with 1,000 kilowatt hours a day, there's a certain flexibility now because it could provide almost 6,000 kilowatt hours, but it only has to take 1,000, which means it can shift around the charging during the day and charge the electric vehicles when it's cheaper or when we have excessive electricity from a PV system or so on. In my case, I'm just going with 5,500, so there's not much flexibility, but that's it here. Any questions? Anything to add, Zach?
No, I don't think so.
Okay, so last thing is the natural gas generator, which we take from a catalog. It's a 6. Okay,
So as you're doing that, Michael, we did have a few questions about CHP. So maybe we want to highlight the CHP components as you're going through it. Okay,
let me do that. So, we model CHP systems, internal combustion engines, just electricity. It's really up to you on how you want to do this. And you can also use multiple fuels. I mean, this engine can run on biogas or natural gas. We can also have hydrogen if it's a fuel cell, right? We can just say, well, this engine is just for backup generation or for regular operation, or it's a CHP system or just an electric system, right? And then if it's allowed to export to the utility or not. So these are basic parameters here. I'm going with natural gas CHP. And since it's CHP, we have a heat to power ratio, which means how much. So this basically tells us that we get 1.786 kilowatts of heat from 1 kilowatt electricity generated. Here's also the electric efficiency. If you really want to model CHP systems in a very careful way, you can also model non-linear efficiency curves. Depending on the loading, of course, they change. So let me define something like this. And then depending on the point where you are, of course, the fuel consumption will change. You can do the same thing for the heat to power ratio because they're linked. Electric efficiency and heat to power ratio is, of course, linked, right? So you would also modify this here. In other details here, are really minimum loading. So some generators don't like if you go below 20% loading, then they would have to turn off, right? So you could actually model this here. Activation demand, for backup reasons, whatever it is, you could say if my load reaches a certain threshold, that engine would have to kick in. The sprint capacity and sprint hours. So some manufacturers allow you to go above the nameplate capacity for certain hours. We can model this. There is maximum annual operational hours, could be used for air regulation. Maybe some generators are only allowed to run for 164 hours, whatever it is, right? Ramp rates, how quickly an engine can respond, especially for market participation. And then, of course, minimum up and down time. This is really, really important also for some fuel cell technologies, because if you turn them off, then they should stay off for a certain period of time, otherwise they get damaged. So to avoid cycling of technologies here, we could actually set this minimum up and down times here. Does this cover all your questions, or is there anything else you want to know here?
No, I think that covers it.
Okay. Okay, so let me make sure that I defined everything correctly here. Save it. So now we're ready to go. So we now gave Xendee the information on technologies, electricity rates, and load profiles, and now it's really to figure out how much costs we can save, how much CO2 we can save, depending on our objective. And we do this by clicking on main here. Oops, optimize. And the first run that we're doing, is really a cost minimization run. So we're just interested in cost reduction. I'm not using the detailed data that we uploaded because of runtime. So as Zach was explaining to you, this down sample to our typical profiles for every month. They have two advantages. First of all, they take out uncertainty and volatility. The second thing is also that they can improve runtime here. And this is why I'm going with them. But I mean, and I will also run at times, so you will see the differences here. But just to give you a result here, we just use this downsampled average data. And this run takes maybe 10, 15 seconds to solve in the background. One thing, this is all cloud-based. And by the way, we are DoD certified now. So we went through and SAC most stuff at most for that through a process with DoD to really be secure here, and we tested this for a couple of DoD projects here, and basically everything is under on Rackspace. Rackspace is DoD certified, and it's completely locked down and also separated from the commercial space. So every customer group gets a secure server, and so that we're also not mixing data and so on. But at the end of the day, we do this also for the Navy, for the Army in Europe, and also here for the Navy in San Diego, also on the East Coast.
And I think that's a key point, Michael. I mean, you mentioned Rackspace. So everything we do is cloud-based. You don't have to have any special operating system. You just have to have a connection to the internet, regardless of what browser you use. It'll work the same, and it runs on our computers, which are, again, state-of-the-art Rackspace processing units that we host ourselves.
That's right. That's right. So what Xendee did now is it actually ran two cases here, a reference case and an investment case. The reference case is basically all the energy is coming from the utility plus any existing technology. So I modeled the electric chiller and the boiler as existing technologies, and this gives us this $5 million. With these investments here on the right-hand side, we can bring the costs down by 44%. Carbon emissions go up, and this is probably because we have actually a huge CHP system which runs on natural gas in this case, right? But as you can see, OPEX savings against utilities, 72%. We have all kinds of different definitions for all these indices, but at the end of the day, I mean, in this case, it's a 6-year payback period for this project. If we scroll down here, it tells you exactly where we are making the money. So these are the revenue streams on the left that are implicitly considered through the tariff, through the rebates, and what we defined. And I mean, most money we're making through energy charge reduction, time of use rate management, demand charges, and then there's some SGIP, which are obviously turned on, and technology tax rebates that bring it in. There's also a virtual utility bill, which shows you how you're doing now. So, I mean, the reference case, this was the original utility bill. Now we're at $1.3 million, and it shows you, in this case, we're not purchasing a lot of natural gas because we have the CHP system, right? Oops, I closed this by accident. If we financial data, it shows you how the micro performs in every month. On the left-hand side, we have the reference case. On the right-hand side, we have the investment case, which is composed now by investment cost, operation maintenance cost. As you can see, this is really attractive case because we're always lower than the left bar here. And there's also cash flow tables and all that stuff if you scroll down. But one thing I really want to point out to you is really the dispatch here. Let me just find a good month here. Let's go with a September day with a peak. And this is something which I really want to point out here. Xendee tells you on how to run the technologies, or you should plan to run the technologies. And I was focused on cost minimization. And of course, most people would think that, well, we have a PV system, we'll charge the batteries for the PV system, and then we use it when the PV is gone in the evening, right? But what we can see here is actually, because we have a combined heat and power system, which also has to supply energy on the heating side, it's actually attractive to run the CHP system, these blue bars, almost flat, and then use excessive electricity here in the morning to charge the battery, and then discharge it before the sun kicks in. So actually, most of the energy in September comes in the battery, comes from a CHP system and not from the PV system. If we flip actually the objective function, which I will do now, to a CO2 minimization, probably this will change it, and we'll see a different behavior. So what we do now is we say, okay, this is actually a third run because I will do the second one after this. Based on my script here, so we do a CO2 minimization with a premium cost factor. And that's important here because we focus on CO2 reduction, but we want to tell also the system that we're still focusing a little bit on cost, right? And in this case, it means that we allow 20% higher costs than in the reference case in the current situation. So we want to drive down the CO2 emissions, but at the same time, we also say, well, probably we'll see more expensive solutions. So let's allow for more cost here. I have to change one thing first. In the PV part, I will increase the available space for PV because I know already that we're maxing out on the PV space if I'm not doing that. So reduce CO2 1.2. Good run, and let's run it. Anything that came up on your side, Zach, that I should tackle here?
Maybe you want to just talk about the databases that we have and just for the different assets.
That's right. That's right. I didn't do that. So databases. We have three databases. One is your own database, which is just private to you. You have a project team database, which is private to your team. And we have Xendee catalog, which is open for everyone. And what we have seen is actually that, let's say you would purchase this, you would work with Xendee and you have your own team, and your team has 3 people, one does screening, one does conceptual design, and the other person does engineering. Then you could actually move the projects between those persons, and they could use the team catalog. If you build your own catalog, you can use it. And the Xendee catalog is actually really the starting point that we are providing here. And we have this for most technologies. We also upgraded it most recently for other locations in Europe, Canada, Australia, and South Africa, for example. So the CO2 minimization has been completed. And now it looks a little bit different, if you remember. I mean, we now only show a 9% cost reduction, but we show a 27.5% CO2 reduction. The CHP system is not going away. It's still there, and it's probably because we have also the heating side. The battery is also smaller, and the PV went up. And this is really another interesting thing. Because when you charge a battery or discharge a battery, you lose energy because it has a charging and discharging efficiency, right? So it's probably with a CO2 minimization goal better to use the electricity directly from the PV system than always put it in a battery system. And I think this is what we're seeing here. So if I go dispatch here to, what was a September peak, probably, you see that actually the battery is not doing anything. It's sitting at the minimum state of the charge at this day. And we have just a larger PV system, which directly gets utilized to bring the CO2 emissions down. How does it look like in February? Yeah, the battery is not really doing much because in this case, batteries would introduce actually some inefficiencies. On the CHP side, heating, as you can see, now everything is still running on the gas boiler. There's some. Most things are running all the time. Actually, is running on the CHP system, except here in the morning from 6 to 9. There's some additional gas boiler because it seems like that the 633 kilowatts are not really big enough for this spike here in the morning. But still, this is the driver, and this is why we still have the CHP system in the solution, because it's the heating side. One thing I want to show you, I'm not sure how much time we have left, 9 minutes. I ran also already a full time series optimization. Let me show you this, because I always ran this now with the downsample data with this peak, week, and a week profiles. But if I run this with the full data set, I get actually the dispatch for every day. And this is what you see on the screen here. You can see I can actually go through every day here and check out how the system would actually be working. In this case, again, batteries probably not that very attractive and not used that much, as you can see. But the point is really, you see for every day a dispatch profile. This is why we have also a control system at our hand, because we can combine this with real-time information when the technologies are installed and then control the technologies. So let me just show you 2 things. Let me just take out the PV again with 140,000. So we can also model outages. And Zach, maybe you want to explain this briefly here.
Yeah, so I mean, as anybody who works with microgrids know, right, there's two major value streams. One is cost, which is probably the rarer one that a microgrid makes sense for cost. The other one, the major one, is resilience. And this is where, you know, the Department of Defense has really identified themselves as in the resilience space. The point is, what does resilience mean? Resilience means responding to outages, responding to contingencies where you don't have power, and having the microgrid actually become a microgrid. So the way we model that is through specifying specific outages and letting Xendee know what assets will be available and how it should respond. So what Michael's showing you is we can either just have Xendee pick the day, or we can put in an exact date. So if you know you want to, you know, plan for a wildfire, put that date in when you expect the wildfire to happen. Otherwise, let Xendee choose kind of the worst time. And you can also model scenarios. So as Michael's showing, you know, you can say if we have a wildfire, maybe there's smoke and the solar won't be 100% available. So we can reduce it to, for example, 50% to account for smoke.
Right. In this case, I'm going really with a simple way. So just telling Xendee, hey, I want to sustain a 3D outage. Please tell me if, with the technologies that you're considering, how much it costs to do this. And I'm just running this over the cost. So this is the fourth run. We do cost reduction, we do resilience, and we just kick it in. Should take another 15 seconds. If I haven't done anything wrong here, it should come back with very similar technology adoption like we have seen before. Because of the gas generator, we are probably completely independent for 3 days if it's needed. Okay, while this, oh, here we are. Okay, show optimization results. And yeah, Xendee tells us that there are no increased costs needed for this 100% write-through capability for his 3 days. And it actually has exactly the same solution which what we started with, because with this PV system, this battery and this gas generator, we actually can have 100% write-through capability. Let's check in August outage day here. And as you can see, it's using the battery here. And then at the same time, the CHP system, and then it actually uses the CHP system again to charge the battery up again. So it's, I mean, it's completely independent. As Zach said, we could have also played with the PV output. I mean, if we would have said we expected there's no PV output, then let's do this. Maybe this is changing then our solution. Let's see if it's doing something. Oh, man. Come on. Where's the outages? Here we go. Let's say we have no PV available because it's really it's wildfire and there's so much smoke in the air. So then and let's do this. So while this is running, there's one last thing I have for you today, which is the multi-year setup. And the multi-year setup actually allows you to not only consider 1 year as we did until now. It's really, you can model changes in storage costs and technology costs, right? I could say, well, what's happening if the cost of batteries are going down by 5%? I could specify this in a very detailed way for every year if I want to do this, but I'm not doing this now. Just cancel this. What if there is a performance degradation for the battery? Let's say it's a 1% degradation. What if the electricity, the demand charge costs are going up? Let's say it goes up by 2%, right? What if the fuel prices are changing and so on? And then I can actually select what year I'm considering here. In this case that I'm selected here, I'm looking into every year to figure out if an upgrade to the system is meaningful or not. I'm not sure if you go back every year and really check to upgrade the battery or so, but it would tell you basically what you can expect from all these changes. And if we run this in this multi-year fashion, which takes longer now because of course we are going with 20 years here, just show you here the multi-year result. Then you get results for every year. I can drill in for every year like before. But oops, what happened? What happened here? Results. Where's the multi-year? then if I drill in, then I see the results as you have seen them already for every year. But what is really cool is it shows me how the capacity is changing over time here. I'm not sure what I did here, but in this case, it seems, oh, that's the wrong case that I'm showing here. I want to show you probably this one. You see how the battery is changing over time. So basically it tells us that we should start with 1.2 megawatt hours in year 21, but then at the end of our project lifetime, we should get 3.6 megawatt hours. So I mean, you're probably not going to start, so you're probably not going to back every year here and change the battery setup, but you know that maybe you undersizing the battery if you stick at this to this size, or maybe you're oversizing if you would start with this battery size here, right? So depending on how you see this, you can actually determine how much money you're losing. So this is actually the last thing I want to show you here. No, actually, let's see how this changed here in terms of outages, because I was modeling less PV, and still we don't have to add more technologies here, so we're still good. Okay, so that's all I got here.
Excellent. Michael, thank you so much for sharing, and thank you everybody for being in attendance today. We really appreciate this. As a reminder, a recording of this event will be sent out. So you feel free to follow up with that and maybe work through it again if you fell behind or want to go through this process again. Additionally, the same email address that invited you to this event, Brett, who's on camera with us right now, feel free to reach out to Brett to get you started on your account. Anybody who was in attendance today or in attendance in our live event, we welcome you to come get a free trial of Xendee. That was a 1-month free trial, but it started at the beginning of the month. So you'll have that through the end of this month. And we really welcome you to get online and check things out and experiment with that. Once again, just follow up with, he just posted in the chat as well, but bmiller@xendee.com. That was the same email that sent you these invites. And he'll be happy to either continue the conversation about Xendee or get you started on that free trial. Additionally, yeah, reach out to Brett and make sure that if you have any questions or anything else where you want to cover how Xendee can really meet the needs of your organization, feel free to get in contact with him at that address. He can also answer your engineering questions or make sure you get put in contact with the right person. So once again, thank you everybody for your time. I really appreciate engineering's time here as well. And it will send out a recording to everyone. Thank you so much for your time. We'll talk to you all soon.
Thank you. Have a good afternoon. Bye.